All right. So now we're going back to computer science and the coding phase versus the execution phase. In fact, I think at some point I had down here compile phase and run phase, and then I did global changes, and I don't quite remember why, but there was something that muddled people. All right. So here's, I guess, the compiler implies the compiler's doing it, and the coding implies this is what I'm doing before I give it to the compiler, right? So, and what's the big split here? What's the history? Some boss gives me the free variable values, right? We want to know, is this true over every model, right? So the free variables, you could think about it being given, P being given to me by an adversary, or you could think about it as it's being given to me by my boss who wants, right? Or it could, or your boss could be your adversary, you know? I mean, it's all, anyway, somebody gives me P, and now we want to, given P, we want to know, is it true or not, right? And so the prover comes up with the algorithm, and the adversary comes up with the input, and we check, right? And this here is called the coding phase. And this, it doesn't depend on the input, right? In this part here, right, here we got compile errors, right? And here, the execution phase, it completely depends on the input, right? Everybody get that? Runtime errors. All right, so how does it go? He constructs an algorithm without knowing the input. It's got to work for every input. And what does he fix at these times, right? He fixes what his Java code is. He fixes what variables that have names he fixes, right? He fixes how many lines of code there are, right? What data structures are you going to use? And then the adversary comes up with the input knowing all of that, right? His input can be bigger, of course, and it's, right? It could require a lot more computation. It requires a lot more space, right? So what happens after the input comes is you run it, right? And when you run it, how do you handle memory? If you need more memory, what do? You allocate more memory. And how do you keep track of it? You have pointers pointing at it, right? So the way Turing handled it is compile time memory was in the states. You had more states of your Turing machine, which I don't know if you haven't done Turing machines yet, right? And then the way he handled runtime memory is he had this infinite tape, right? And how did you get to it? You have to walk to it, right? So if I would go back in time, Turing, I would say, hey, Turing, dates are a little confusing for my first-year students. Why don't you write code, and why don't you have variable names? And then why don't you use allocation and pointers, right? He didn't know that. All right, everybody good? All right, right, so his Java program has some number of lines. All right, so these questions, what we're going to be doing now is one, it's in the slides. Two, it was on an assignment/test years ago. I think you have it's available somewhere. And I can imagine having a section of sort of quick, what does this mean, and is it true or not? And I'm going to have to come up with a lot of them if they're going to be a little section. And these are nice ones, right? So you know, we know Java code has a number of lines of code, right? And so a Gödel wants to put everything into logic. So here he says, here's a thing that takes in, it's a function. It takes in two objects and returns an object. And this object is the algorithm. This input is the input to the algorithm. This input, this here, is how many lines of code it has, right? And hopefully everyone is saying, why do you have I in there? Because the number of lines of code doesn't depend on the input, right? Were you all thinking that, right? Well, why did I put it in there? So that we could say that, right? Right? But it doesn't depend on the input, right? But we want to say it doesn't depend on the input, right? So we put it in there, right? In contrast, the running time of the program, right? Here we can say, given an algorithm and the input, how much time does it take till it halts? That does depend on the input, right? Running time matters, right? So here we're going to put in our statements, right? Everybody buy that? And now it's not quite a good statement because right now P is free and K and T are free, right? So surely we don't want K and T to be free variables. So we have to add a quantifier, right? And now, do we want this to be true for all Ks? Is this going to equal K for all K? No, there's one K, right? There's one K. And time, does it work for all time? No, there's one halting time, all right? And then we want to say, who does this? We get this at compile time, right? Is this part of the coding phase or the execution phase, right? And the K, right? Who chooses the K? When does it happen, right? It's the coding phase. It doesn't depend on the input. It goes up there, right? Versus the T does depend on the input. It's up there, right? Yeah? The point of this slide is to get you to deeply understand flaws and exist. That's my point of the whole course. No, my goal here is to be able to say things about computer science in logic, right? So we're going to say things that are self-evidently true, and we're going to say them in logic. Why? Because if you wanted to prove these things that are self-evidently true, the way you do it is you write it down in logic, and then you play the game, right? And what's going to happen in your computer science degree is they're going to be proving things, some of them which are self-evidently true, and some of them you don't even understand what they're trying to say. And if you can read a first-order logic sentence and know what it means and be able to play the game, you will be ahead, right? And what examples am I starting with? Statements that are self-evidently obvious, right? And I'd be curious to whether when we go through these examples, whether I'm giving you added knowledge or whether you're like, yeah, dude, I know this. This is easy. And I know the logic. It's easy, right? So, I mean, how many of you could have just written this down versus you're still, how many of you just think this is so obvious? How many of you feel, hey, going over this is useful? All right, that's what we're doing. All right? I mean, so what's the game here, right? In fact, we're going to play the game, right? Right? We can't switch the order, right? I mean, here, the order between these two, if you have two exists, it doesn't matter which order they're in, right? You have two for alls, it doesn't matter which order they're in. All right? So now let's think about what this means. This, right? We have all these free variables, and it's saying A solves P. A has with K lines and T time, right? What were its resources? Here it did solve the problem, and what resources did it use? It used a certain number of lines of code, right? We could have brought memory in here instead, but this is kind of, memory is split into two pieces. Those that happen at if it has a variable name, it happens at coding time, and if it's malloc, it happens at runtime. And so these are clear cut what's happening, right? That's why I did these, right? Right. So solves. Why do I say solves might be overstating? Because we're only saying it does it on this input, right? Right. So here, this is just saying this algorithm here solves it on 5, right? They keep coming back to the same sort of things. All right. I don't know what that. Oh, time. That's time. Broken clocks are twice, correct twice a day. All right. So here, what are we saying here? Is we're saying now for all inputs it solves it, right? So now we can drop. We just need to talk about the free variables, right? What does it say about P, A, P, and T, A, P, and K, right? It says A solves P. I'm not talking about the input, right? So the implication is it solves it on all inputs. And how much time? Well, it solves it. That means it halts. That means there's some time in which it halts, right? I mean, what are we adding to this? We're adding the fact that if you're going to solve it, you had to have halted, right? And right, it does. Right here is just adding, and it depends on the time in the input, right? Then we add this bit here. We say it's computable, right? Everybody good with this? Right. So as this is, in fact, what are these sentences? When I gave them the test question, this was the test question. I said, what I did is I gave them some math formal like this, and what did I ask, right? If I ask you, what does this mean? And you say, it means that there exists an algorithm for there exists a K, right? If you just read it, you're going to get 0 marks, right? So I'm trying to say, what do you need beyond that, right? You should understand the game that proves it. You should understand who's providing what. You should be able to explain, right? How this value depends on this value, like the time depends on the input, right? You got it. But K does, right? What's the point of this? Is that time depends on the input and K doesn't, right? So if I were to read this and out of the blue and say, what would I say that this says, right? I would say what it says, P is my free variable. So this is saying something about P. It's saying that P is computable, right? But when it's computable, it needs a finite amount of lines of code, and it needs to halt in a finite amount of time, and the time depends on the input, but the number of lines of code doesn't depend on the input, right? So you see there's a lot in there, right? Everybody see that? There's a lot of computer science is in that sentence, right? And you need to be able to extract all that information out of this sentence, right? Does that make sense? All right. So, right, this is just the game again. How do we prove it? The algorithm comes up, the prover comes up with the algorithm and the number of lines of code and its variables. He comes, right? He's coding it, right? He doesn't know the input, right? You all know this already, right? Right? When he comes up with the code, it has some number of lines in it. We denote it by K, right? And then the adversary, he's trying to make it false. He comes up with the input. And the inputs, if you give a big and big and big scary algorithm, he's going to give you a bigger and bigger scary input, right? And then you run the thing, right? And you run your algorithm on your input. And then we get to say, yeah, if you give me an input this big, this is what the running time is, right? In fact, what do we say? We say time is less or equal to the size of the input raised to n, right? It depends on the input. Not n, sorry, 2. Right? And then we have to prove that it gives the right answer and it uses the right amount of time and lines of code. Right? Everybody good? Any questions about this? You feel you could do one of these? Right? Is the statement true or false? Explain. Right? Well, if P is computable, then it's true. Right? Right? We just give the algorithm that can compute it. And if P is uncomputable, right, then right, if it's uncomputable, then it's false, right? He tries to come up with an algorithm, but the algorithm's not good. Any algorithm he comes up with, right, the adversary knows it's not solvable and can find an input in which the algorithm's going to fail, right? And everybody kind of good with that? And why do I have this many slides? Why? Because it was a test and they wanted me to take it up. In fact, if I'm not mistaken, it was all during COVID. So everything I got more slides made during COVID, right? Because we were. All right, so here's some more, right? Pretend it's a test. Read this and see what it says. Do you get what it says? Yeah, you're kind of reading it, but I mean, it's. I mean, let's do the game. Yep.
That produces. Sorry. There is an algorithm of each number of lines.
Yeah, of each length. Yeah, exactly. Right? What does it say? You can. In fact, I'm gonna go make it a little bit more friendly. You can make your code as long as you want. Right? And that length won't depend on the input. Right? We get an extra twist in there. Right? So this, I mean, I turn it into a conversation, right? Adversary gives me a K, and I give the adversary an algorithm, right? It's sort of like, in that form, it would say, I will make you an algorithm as long as you want me to make it, right? Your boss says, I want a 1,000,000-line algorithm, then I will watch the movie The Shining and say Jack is a fine boy or something, and I'll write it over and over and over again. Oh yeah, maybe that's it. Anyway, it's a scary movie if you haven't seen it. And he's working on a book. Right, everybody get that? So what are we saying? Right? Right? Algorithm on an input has a certain lines of code. What does this say? Let's say it doesn't depend on the number of lines of code. What does this say? This says, what does it say about K? I remember how we would bring this out like this? What does this say about K? Right? It says I can make an algorithm that has length K. You see how that helps us understand it? You roll it out, you say, this sentence has to say something about K. And what does it say? I can say, Jack is, whatever the line is, I can say it K times. Right? And now what does this say? It says, any K I can do it for. Right? And you know what I was doing here? I'm trying to write down random for all exist statements and seeing if they're useful. Right? In fact, that's what I'm going to do on the test. I think we're going to have a section where there's just random for all exist statements. You have to parse out a little bit about what it means, right? And say whether it's true or not in the model that we're talking about or in all models, right? So really, how would you do it is I really would sort of look at this line and say, what does this say about K? Right? You're telling me that every K has some property, right? Okay, forget the for all. What does it say about K? It says I can build a code that length, right? Everybody good? Yeah, you good? Everybody, yeah, right? Here's just, I was throwing these in periodically, right? You give me an eye, right? I don't know. What's the game? Adversary gives me a K, right? Right? The adversary gets to choose the K this time, right? Before, we were saying there exists a K, right? You give me an algorithm, there exists a K. Now I'm saying any K. Here's a bijection. Every algorithm has a K. Every K has at least one algorithm, right? We're doing a bijection between the Ks and the algorithms, right? It could be that this is false because for some reason you can make codes of length 4 and 6, but 5, no, we don't, right? We don't let you do codes of length 5, right? Everybody you can, good? It's just a game and I'm chatting about it, right? Right, so how do you play the game? We've done the game already, right? Everybody got the game? Yeah?
About showing that the lines, that K does not depend on I. Then how do we go about showing?
Yeah, so let me do a meta question, answer that in a meta way. For this section of stuff, we're not going to really be focusing on what are we proving about, right? If I give you a question about graphs, hopefully I give you a question where I don't ask you anything about graphs that isn't really obvious, right? You know the topic, right? So do you have to, right? Even if I said in the way we're doing the algebra ones, there exists a 0. Well, there's a 0. We're not asking you to go back to the axioms of real numbers to know there's a 0, right? You can just say, hey, there's a 0. And one thing I'm expecting everybody in the room to know is that when you change the input, it doesn't change the length of your code. We just all know that, and we can state it.
Right, but if you were to take off the context of it being lines here, right?
Yeah.
Then that logical statement, that would still result in K not being dependent on I, right? So
yeah, so if here's on a test, what am I going to ask you about? I'm only going to ask you about things that I think you know, right? So if we replace lines by time, right? Would it be true if I replace lines by time? No, it's not true, right? It's not true, because if you give me, I mean, let's do time. If you say for all t, you give me a time, I'm perfectly willing to say there exists an algorithm and there exists the time that's that time on the algorithm on this input is t. Is that true? Yeah, that's true. You give me a time, 5,000,003 seconds, right? I could do some sort of binary search, right, and find this, that it's going to be true, right? But if we change that to this, it's just not true. Why? Because how do we prove it's the adversary can say t is 10 and then come up, and now, right? Well, actually, this might be true still. Oh, what? There's two t's. There's two t's. All right, this one was input. That's what we're doing. Actually, I take it back. This is true. All right? But how many people want to think it's true or not true? I'm voting true.
Oh, that's true.
Yeah, exactly. That's how we do these things, right? Anybody want to argue it's true?
Yeah, but only one algorithm has to exist. You could have like an algorithm that.
Right? This makes me nervous that I'm saying for all inputs, the algorithm, the running time is fixed, right? Why might it be true? I get to choose the algorithm, right? And here's, you give me it, here I'm going to prove it's true.
There's certain things that are not computable in like a fraction of a second if it's really small.
Yeah, let's say this is an integer. I don't know, greater than 0. Yeah, so I'm gonna, let's define time to be the number of ops that happen, right? And not the number of seconds, right? So then you give me a time, and I'm going to design an algorithm. What does my algorithm do? It ignores the input, and I loop t times doing an op, right? Everybody buy this, right? Yeah, you tell me a t, I write an algorithm that does t ops and doesn't depend on the input.
Input's just there going along for the ride.
It's going along for the ride. Yeah?
That's what I was asking before, because if you were to replace time with just like say alpha, is that true? Like is always true? Does it not depend on the last one? The last one's it's a for all.
Yeah. And my answer is it's subtle. And hopefully I'll ask you questions where you know the answer. Right? Is this easy? No, no one's claiming this is easy. Right?
What you're saying is happening kind of twisted, right? Like time versus ops.
Yeah.
There's definitions, premises.
Yeah. All right. But again, I've taken more computer science, and I know that most computer scientists define time to be ops and not seconds. Right? Right? Because when Turing built his machine, one op took an hour. Right? So yeah, if you say, can you run in a second? No, you can't. Right? Right, again, I mean, again, we can go back to, is it true or not, depends on your model. Right? And his model, where time is measured in seconds and my computer's slow, maybe it's not true, right? I think this is a good example. And I would almost say I might not put this on the test because it's a little hard, right? I got it wrong the first time around. I wrote it down to be wrong. People kind of buy this? Right, so here is the, right? This is the answer I gave. I said it's true. Why? Because an algorithm designer can build an algorithm with any number of lines of code, and then this number is fixed as the input grows, right? So I would say if I give you this as a question, this is the answer I want. Would everybody agree that this is better? It's a pretty good answer, right? All right, so here's another one. Let's do this one. Again, the adversary is giving us K, right? Right, what did we change? It's the same as before, but you've got to solve the problem, right? Is it true? Right? Think about the game. We're saying, you give me a number of lines of code. And now what am I saying is I can write a Java program with the number of lines of code you're saying to solve the P is a free variable, right? It's some problem, right? Is it true for the halting problem, for example? Does there exist? I don't care about drop K, right? Ooh. Forget about the K. Does there exist an algorithm that I was maybe over here it was better. I was too close to the speaker. All right? Right. So I would say forget K and say this says there's an algorithm that solves the problem for every input. That's not true for sorting, for the halting problem, right? Now what happens if I put in here sorting? Is it true for sorting? Can you write a 3-line program that sorts, right? Well, it depends on it depends on your programming language, right? I hate Java because it makes you put all this fill. You can't write a 3-line hello world program, right? Everybody getting this one? Right? 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 What are we saying out here? P can be computed in any number of lines of code. Well, P might not be computable at all, and sorting might not be computable in 3 lines of code. Right? Everybody good with that? The negation should be true, right? And sometimes when I'm proving it's false, I just play the game in the same way, except I have the adversary win, right? It's the same as negating it, right? Everybody good with this example here, right? Should we go through these details, or you kind of get it? Anybody want more details? Right? I was clearly, right? Why is it false? He gets to come up with K. The adversary is happy. He knows that the problem is computable, maybe sorting. Oh, here's something that at the beginning of the question, I said that P was computable. All right? So now you have to know, is this true when P is computable? So you can't throw in the halting problem. So we know P is computable, but he knows many algorithms that can solve them, right? But P is not that easy, and it takes a minimum number of lines of code to solve it, right? And so he doesn't spend time to come up with the exact minimum. He just says, hey, let K be 2. Can you solve it in 2 lines of code? I dare you, right? Sounds, everybody good with that? Right? Now the prover's unhappy and wants to pout because he can't get a program that he can come up with a program that has 2 lines of code, and he can come up with a program that solves the problem, but he can't come up with a program that solves the problem in 2 lines of code. Right? All right, so we keep doing, here we go. Quick, false. There's some minimum number of lines of code that an algorithm needs below which it can't solve P. Right? People getting that? I mean, that's translating it into English, right? English that you would understand. And what are we trying to learn is if I tell you this, you should be able to write down this. And if I tell you this, you should be able to write down this, right? You should be able to translate between the two, right? You kind of, everybody good? Okay, here's another one. I think we kind of did this one already, right? This mapping between algorithms and lines of code. This one says, you give me an algorithm, I can find the number of lines of code, right? But really, we've never had a for all algorithms before, right? This is our first time I put a for all algorithm, right? What am I saying? Every algorithm has some number of lines of code. Before we were saying there exists an algorithm that has a number of lines of code. Now I'm telling you more, right? I'm telling you every algorithm has some number of lines of code, right?
You're saying that you're expressing any possible algorithm. Like, say you can express, there's at least one K that you can express merge sort in.
Here we don't have any P, right? There's no P.
But in this set of A, it's every single algorithm. So that also includes merge sort, doesn't it? Wouldn't that also include like the real algorithms, like merge sort, for example?
Yeah. This is a set of all algorithms. This is a set of all Ks, right? Before we were saying there exists an algorithm, right? So here's some, right? Before we said for all K, there exists an algorithm. And before we were saying if you say there exists an algorithm and there exists a K, right? But we've never said for all algorithms, right? It could have been before that this algorithm doesn't have a fixed number of lines of code.
Every algorithm has at least one length.
Yeah, it has at least one length, right? I might even go on to say it's unique, but this doesn't say that.
And each algorithm in this case doesn't necessarily work.
Oh, we're not saying even defining work here, right? There's no P, right? Everybody say, I mean, that's how do you do this? How do you translate this into English? You first note what right? You can go through what I'm doing here. Here, right? You first say, what are the free variables? And you'll note there's no P's. We're talking about how many lines of code A has on a given input, right? And then what does this say? Now we're just saying the algorithm versus the K. Now we're just saying algorithm A has K inputs. It doesn't depend on time, right? And now what does this say? Something about the algorithm. What does it say about algorithm A? It says it has some number of lines of code, right? Build it out like this. right? What does this say? Every algorithm has a property. What's the property? It has some number of lines of code, right? Are you guys following this? Okay, here's one, right? This is one we've done before, right? I mean, what does this bit say? Let's see if we wind it out. What does this say? This says, it's talking about three free variables. It says algorithm A solves P on input I, right? Roll it out. What does this say? There exists an algorithm, right? On it, right? The free variables are still I and P. So it's kind of like your boss comes to you with a problem and an input, right? I mean, that's not so unreasonable, right? He's saying, I got York University as a client. That's who your input is. I want you to schedule their courses. So P is course scheduling, and I is York University. Is that computable? Right? Yeah, well, yeah, it's computable. I can just brute force, do an exponential search, find the answer, and it's a Clockwork Orange example, right? There, Clockwork Orange, right? This, you give me the input, I can have an algorithm that just gives the answer. Yeah? It's right, but not nice. Right, in fact, good point. I was thinking about having different levels of, does it say something true, and does it say something that's nice, that's useful? And the problem with that is, what's the definition of useful, right? I say this all the time, so it must be useful. But what's the use is to show you that this is dumb, right? Everybody, right? Right, we've done this one a few times, right? For even undecidable problems, oh, that should be a P, right? It's not a good statement, right? Because you can have a different algorithm for every input. All right. What does this say?
That there is an input that can make any algorithm wrong.
Right, right. So said in English, P is? P is unsolvable, uncomputable, right? This is the negation of P is computable, right? 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 This says A, right here, this says A doesn't solve P. Why? Because there's some input in which it fails to solve P, right? This says P is not computable. Every algorithm fails to solve P, right? So is this true on our test? Yeah, and at the top I said P was computable, right? So right, this says that P is not computable because no algorithm solves it for every input. But I did say on the test that P was computable. Right, everybody good?